Welcome to the ROS introduction course. My name is Peter Fankhauser, and we're here with Professor Marco Hutter, Martin Wermelinger, and Dominic Youth, and we'll guide you next 5 courses through programming for robotics, especially C++ and ROS. This is the overview of the 5 days. In the beginning, we'll start with some of the ROS basics, the ROS architecture, and in the second course, we're going to talk about how you create your own programs and your own ROS nodes. And then course 3 and 4 are additional tools and elements of ROS that are useful when you work with ROS. And on the last day, we'll have one case study from our group, in our group where we use ROS extensively, and we're going to show you what we do with ROS and how far it can go when you use ROS. And today, of course, we'll go through the part 1, the course 1. Now, this is important for the overview. We're here now on Day 1. We'll always have one introductory lecture and then an introduction to the exercise. You'll have the remainder of the time to solve the exercise. And then during this exercise, once you're done, some of them are more easy, some of them are more difficult. Once you're done, you can raise your hands or come up here and show the results. It's important that each of you shows us the results such that we can grade it. The deadline is always the following course early in the morning before the lecture. So today we'll have the lecture 1, exercise introduction, and then you'll solve exercise 1. Each exercise has several check questions. You'll see it in the bottom. And those are the ones we're going to go through when we grade you. We have 5 exercises, and each of them count 20%. We encourage teamwork, but all of you have to show their results either on their personal laptop or on one of the PCs in the back to us individually. Like I said, exercises are checked by the teaching assistants or the latest, the following course in the morning, which means in the morning, 8:15 to 8:45, that's the time where you can come by and show us the exercise. Come early, such that we can start in the lecture on time. This is except for exercise 5, where you'll have to show it at the very end of the course, because that's a shorter one and that's where the course will finish. Let us know once you're done so we can check you gradually, so not everybody comes in 5 minutes before the lecture starts. And important for those who have already shown us that the exercise, the theoretical part will start 8:45. So you can show 8:15 to 8:45, and then for those who have shown it, come here at 8:45. But the best is if you show it during the morning, especially for the easy ones. Just raise your hand, and then we can check on you, and then you can actually leave. Okay. So in course 1, we'll talk about the ROS philosophy, the architecture, to go through the important concepts like the ROS Master, ROS Nodes, and Topics. You'll learn how to use your console to do basic commands and analysis of what's running on your PC. And we talk about how you build your nodes in your system with the catkin workspace. And then in the exercise, you're going to be using launch files and the Gazebo Simulator. So what is ROS? ROS stands for the Robot Operating System. It's not actually an operating system like the ones you have installed with Windows, Mac, or Ubuntu. It's more a middleware that lives between the actual operating system and the program that you write. It has 4 different elements. One is the plumbing, which means that you have multiple programs running, and ROS enables these programs to communicate between each other. Also, it provides a bunch of device drivers that allow you to easily communicate with your hardware. A second part is that there's many basic tools which are important when you work with robots, being it simulations, visualizations, graphical user interface that you can adapt, or basic tools like data logging. So all these tools were written once, and you can reuse them to facilitate your work when you work with robots. There's a bunch of capabilities in ROS, being it for control, planning, perception, mapping, etc. Many people provide to this ecosystem of ROS, so you can make use of existing tools. So if you're an expert in planning, you don't have to write your mapping algorithms yourself. You take some off the shelf and develop your own in your specific area of expertise. And lastly, ROS is a big ecosystem. The software is organized in packages, such as you can easily install and use them. And ROS provides entire software distribution. And there's many, many tutorials, and you're going to work with some of those online available in documentation. For this course, we'll mainly work with the plumbing, the tools in the ecosystem. The capabilities, those are the things you're going to dive more deeply in during a semester work or other work where you go towards the algorithms. We provide you here the basics for ROS, which are the tools into the inter-process communications. A little bit to the history of ROS. It was developed 2007 at the Stanford Artificial Intelligence Laboratory, and then was managed by Willow Garage, was taken over, and then since 2013 is now managed by the Open Source Robotics Foundation. Today, ROS is used by many, many robots, and you see some of them in the videos. These range from universities to companies who use this in their system. It's for research, essentially a standard. It has become a standard for robot programming. And also there is pushes in industry to use ROS extensively. The philosophy of ROS is that you have many programs on your PC, individual ones, which communicate over defined APIs, meaning you have ROS messages and services, etc. Define how my programs communicate with each other. It's a peer-to-peer communication running on your system. Now, since it's peer-to-peer, it can be distributed on multiple PCs. So if you have a robot which has a computer and your computer, they communicate over wireless, and it doesn't matter on which nodes, on which PCs the nodes run, since the APIs and the communication runs also not only on your PC, but also over wireless. So you can build up big distributed system with multiple PCs easily with ROS. It's multilingual, means you can use any of these existing languages which provides a ROS client library. We'll mainly work with C++ in this course, but such that you know, there exists the libraries for Python, MATLAB, and Java, and these can be mixed and matched. It's lightweight in the sense that ROS is not, it provides all the algorithms. The idea is that you take existing standalone libraries and wrap them with the ROS layer such that you enable existing algorithms to communicate and work with other tools together on your robot. And finally, ROS is great because it's free and open source. So to the very core, you can dive in and check for things. And if you find a bug, you can do an issue or actually fix it yourself and do extensions of ROS. So one important element that you'll see is the ROS Workspace Environment. This defines actually the context on where you're working in the ROS environment. There's a standard when you install it, an environment, which is under, if you type in this command, which loads the ROS version and then the environment that you need. And importantly, you can overlay these environments. So in your PC, we already pre-installed one, which we set up in the standard folder, the catkin workspace. And by default, whenever you open a console, we load on your virtual machine that we provided you the standard workspace of your catkin environment with this command. You can check the environment with this command, and you can also see how we set up your PC with this command. So in the future, if you want to install your own PC. So this is already set up. This is only for future reference. Now, one important element is the ROS Master. This manages the communication between your nodes. So at startup, when a node comes up, it needs to register with your master, and the master makes sure that all the nodes can communicate with each other. You can start in the console a ROS Master by just simply typing in ROS core. The ROS core has multiple elements, one of which is the ROS Master. A ROS node is essentially a program that runs on your PC. So it's a single-purpose executable program. You can compile them individually, run them, and manage them individually. So those are the building blocks of your program. These nodes are organized in packages. So whenever we mean a package name, it's essentially the name of the package, and then in there you can have multiple nodes. you see how here in the example, ROS Master, each individual node needs to register with the master such that it enables the communication. To run a node, and you'll use this during the exercise, you type in ROS run, then the package name, and then the name of your executable. Once you've done that, you can look at the list of all the program that runs by typing in ROS node list, which lists you all the active ROS nodes. And then if you need further information, specific information about one of the ROS nodes, you type in ROS node, info, and then the name of the node. And then it spits out all information about the node. How do nodes communicate with each other? They do it through ROS Topics. So one node can publish and subscribe to a topic. And essentially, a topic is a stream of messages that are transferred between the nodes. So in this example, once the nodes 1 and 2 have registered with the ROS Master, the node 1 can tell, okay, I'm a publisher on this topic. And ROS node 2 can subscribe to this topic. So the message flows from the publisher to the subscriber. And the ROS Master makes sure to inform about this connection. So the publisher publishes on a topic name, which is the name under which these messages are published. And then you can have not only one, but multiple nodes that subscribe to this information. But typically it flows from one node to n other nodes. To look at the list that you have provided by the nodes that run on your system, you can type in ROS topic list, gives you a list of all the topics. You can already in the console, you can subscribe to a topic by typing in ROS topic echo, so it's printing out information, and then the topic name. This will subscribe to this topic and show you the contents on the console. And if you need information about a topic, again, like with the notes, you type in ROS topic info and then the topic name. I always provide here links to the documentation of ROS. So if you need further information, you can download the PDF from our website from these slides, type it in or click on it, and you get much more in-depth information on these specific topics. Now on these ROS topics, the nodes publish messages. So essentially the message defines the data structure of the information that flows from one node to the others. It's comprised of simple types such as integers, floats, booleans, strings, etc., and also arrays of these objects. And they can be nested, so one message can be included in the other one, and we'll see an example in a second. If you have a topic, you need to know the type of it. You can type in ROS topic type, and then the node name, the topic name, sorry. And if you need to publish on the topic, so if there's a subscriber, but you don't have the node yet that publishes it, you can publish from the console as a tool with ROS topic pub for publishing, then the topic name, then you type in the type, and then if you click tab is a very important command. It auto completes the rest of the structure such that you can replace the arguments very easily and then publish on this topic from your console. So in this example, we have the publisher publishes on a topic, and the topic is inherently coupled with a message definition. Here's an example of a message definition, which in this case comes from the package geometry messages and is of the type point message. So this is essentially a text file with the ending .msg message, and within this file you can easily read the contents of it yourself and write your own messages. So in this case we have four floats, 64 doubles with the coordinates x, y, and z. Here's another example, more complicated, from the sensor messages topic. This is an image. So on the top you'll have a header, which means there's a sequence number, a timestamp, and the frame ID. Sometimes this is important if you have geometrical information to associate it with a frame. And then you have height, width of an image, and then information about the encoding of the image, and then as an array, the data of the image itself. Of course, you can print this in the console, but it's not going to show as an image. There's other tools for that we learn later. In this example, again, we have a header. So this is a pose message. A pose is comprised of a position and an orientation. And here we say, okay, the pose, we have a position X, Y, Z, and the rotation is here given as a quaternion with 4 numbers. As you can see, this message is comprised of another message type. So the point defines here the position. So these messages can be nested into each other, making it very easy to create new ones and building up on other standards. Now for the people who are running already, it's not very fundamental, but for people who want to try, they can open up their virtual machine and open up a console so we can go through some very basic exercises here together. But this is not part of the official exercise, just for trying a little bit out. So you can open a console on the left-hand side. See a little black box, Terminator. And then you can create, in one of these consoles, you can create multiple views by right-clicking into it and then say split horizontally or vertically, or you can create multiple tabs. And we're going to use 4 of these windows or tabs in this exercise. So in the tab number 1, you can type in ROS Core to start to ROS Core, ROS Master. And you should see the output like seen here on the right-hand side. Okay. Now open a tab number 2 or split the window. And in this console, we're going to type in, we're going to run a talker node, which is already a tutorial which is pre-installed in your system. You can type in ROS run to start the node, and then ROS CPP on the line tutorials, just a package name, and then talker for the node name. Once you are running this node on the right-hand side or in your console, you should see that the node is running and spitting out hello world 0 and with an increasing number. Essentially, this node spits out this message in the console. Okay. Now you're going to open console number 3. We're going to look at what is happening right now in your system. So by typing in ROS node list, you should see the node which you just started in console number 2. So if you do ROS node list in a console, you should see that you have here your talker node that you just started. Now, if you want to know more information about the talker node, you can type in ROS node info/talker, which is the name of your node. And then you'll see that you have the node talker, which publishes on the topic chatter of the type string. So essentially, this node spits out on your console this message, but also provides a topic called /chatter, where the same information is published to ROS. Now, to know more about this topic, you can type in ROS topic info/chatter to see that there's one publisher, the talker node here, and there's no subscriber yet. So this message is just sent out to nobody yet. So we have started the ROS core. We opened up the talker node and we looked at the node. We analyzed it. Can look now more closely onto the chatter topic which your talker is publishing. You can do this by ROS topic type and then the chatter node, which tells you, okay, this topic is of type standard messages string. You can look at the contents now of this topic by typing in ROS topic echo/chatter, which then, similar to your console number 2, prints you the contents of this topic into your console. You should see the message going up with increasing number. Now there's other commands such as ROS topic HZ or Hertz, which provides you the frequency of which this topic is published. So if you type in ROS topic HZ/chatter, you'll see that it measures for a while and then gives you the average rate together with a min and max and standard deviation, how fast are these messages sent out on this topic. Now we have the talker node, it's running, it's publishing on this chatter topic, and now we want to start up a listener. So a node that subscribes on this topic. So you can do this by, again, in console number 4, a new console, by ROS run, and then ROS CPP tutorials, and then instead of talker, now we'll use the listener. And these nodes already know on which topic the other one is subscribing, since it's a tutorial. And then you should see now, once you start this node, that it spits out, it says, I heard, so it's subscribed to this message, and spits out the contents of it. So it says, I heard, hello world, some number. Now to see that these two nodes are now working together, you can go back, leave them running, and go back to your console number 3, where you analyze things. And then you can, again, same command as before, by ROS node list. Before we only had the talker. Now you'll also see that you started the listener and you have these two nodes running. If you now do the same command as before by typing in ROS topic info/chatter, which gives you information about this topic, you see now that we have one publisher, the talker, and now the newly created subscriber called listener. So these two nodes are now connected through this chatter topic. Now we're going to close the talker node. So we lose essentially the guy who gives the information by going into console number 2 where you started it and typing in Control C together. Then you should see that the listener node stops publishing messages since it's not retrieving any. What we want to do now is in console number 2 or 3, publish your own message. This is a little bit a longer command, and you can type in ROS topic pub for publishing on the topic /chatter of type standard messages /string. And then if you use the tab button, it gives you this structure where you can fill in any message that you want to publish. Here in this example, I filled in ETH Zurich ROS course. Now, if you type in this command in console number 4, where the listener runs, you should see instead of hello world, it suddenly tells you, okay, this is a message I got. That's the one you publish from your console. What you saw that you can subscribe to topics and show the contents in the console, but also you can publish messages from your console. Now, we played around with some of the console commands, and I'm going to talk a little bit about the ROS build system. Essentially, this is the system where when you write or you download a package, you write your own nodes, how you're going to build your executables, your libraries, and the interfaces. The standard way of ROS so far has been the catkin make command. But we suggest the much better tool, the catkin command line tools. This is already pre-installed on your system. It's very similar, how it provides nice functionality. So whenever you see in a tutorial on the web catkin make command, it's important you're going to type in catkin space build. Instead of catkin underline make, type in catkin build, which is fundamentally the same thing, but don't mix these two commands. I suggest you use this catkin build command and the commands that I'm going to show you in a second. Okay? So you can typically, when you want to build a node, you would have to go to your catkin workspace by cd and then going into a catkin workspace. And then you can build a package by catkin build and then the package name. Now here's a very important part. Whenever you build a new package, your system should know about it, or must know about it in order for you to use it. So you have to resource your console. You can either open a new console, but it's simply you can type in source, and then if you're in this folder, devel folder /setup dash. This scans again your environment to make sure that your new node, that the system is aware of your new node, your new package. Now, once you build your Catkin workspace, you'll see that you have 3 folders in there. One is the source folder, a build folder, and the devel folder. The source folder is where you put all your source code information. And the build folder is essentially a cache folder for the CMake system. And the devel is where it puts the executables before, if you install them, before installing them or for you to use. Now, these 2 folders are taken care of by the Catkin build system. It puts all the information there and makes sure it runs. So you don't typically never touch these 2. You do all your work in the source folder where your source information is stored. If you run into troubles once that something is mixed up, you change too many things and you're not sure, you want to build from scratch, you can type in catkin clean, which wipes out the build and the devel folder. It doesn't touch your source folder, but then you can rebuild from scratch again. There's a setup associated with your catkin configuration, and you can look it up by typing in catkin config. In the virtual machine that you got, we already set up, and if you type in catkin config, you should see this output. One of the important parts are these CMake arguments. We already set this up, but for future reference, you can set them by catkin build, and then CMake args, and then you type in all the arguments that you need. For example, if you want to build in debug or release mode, if you want to create the Eclipse project files, etc. So there's nothing for you to do right now, but just so you know in the future. Now we come to a second example. And what I'd like to do is go, let's say, on a typical GitHub website and make you clone a Git repository. This is a typical tool that you'll see when working with software. And then we're going to build this on your system. So you can go on the website github.com/etiz-asl/ROS best practices. We put up there an example ROS package for you to play around with. Once you're on this website, there's a green button which says clone or download. And copy this URL here. Then you'll see in your system that you have a Git folder. Just go into CD from your home folder, you go into CD Git. And this is where we're going to clone now. The software cloning means essentially downloading the software in a Git format. You can type in git clone and copy paste the URL. In a console, you can paste by Control-Shift-V. So instead of just Control-V, you type in Control-Shift-V. If you press enter, this will clone all the information from this repository into your system. Now you've seen that we put this into the Git folder. It's nice if you have multiple workspaces in the future that you have one main folder where you store all this when you clone all the software. So that's why we put it into Git. And then what we're going to do now to work with it, you'll have to symlink it into your Catkin workspace. You could also directly clone it to your Catkin workspace, but we recommend you to put it first in your Git and then symlink it in your Catkin workspace. Now to symlink it, you would type in ln -s to create a symbolic link and then tell it from where to where. So in this case, you would say in the Git folder, the ROS best practices, you want to link into your Catkin source folder. Okay, now after symlinking, you should see in your catkin /source a folder, the ROS best practices folder. Okay. Now, once you have cloned and symlinked it in your catkin workspace, you can go to your catkin workspace by cd catkin workspace, and then use the build command, as we saw before, by typing in catkin space build space ROS package template. This is the package which is stored in the Git repository. What you should see is, what you get here on the right-hand side, is that it builds these and it shows information how long it took. Now, since we downloaded, we cloned the new repository. Like I said, you need to source your workspace. You need to inform the workspace that you have something new. You would type in source/devel setup.bash. This is an important step, and if you find yourself at some point that your catkin workspace doesn't find your package, just type in this command again to make sure that all the information is up to date. Now we have cloned this repository, we've built it, and you can start it now. We haven't seen this, but we'll see in a second. Instead of ROS run, you can do now ROS Launch, which is a similar topic, and we'll see what the difference is. So you can do ROS Launch, and ROS package template, which is the package name, and then ROS package template.launch, which is the name of the launch file that you use. If you type this in, and again use the tab command to make it very quick, you should see a ROS core starting and two nodes, or one node actually starting and saying successfully launched the node. So if you go through this, you've seen that you can take source code from the internet, clone it, build it, and run it. These are all the necessary steps that you need to do that. Yes?
Can we go over the steps again quick for me, like first?
Okay. So what we did is you can have multiple workspaces. So this catkin workspace, you have now only one in your system. But in the future, you'll see you might have multiple, right? So if you work in this class, you might have a semester thesis. You don't want to mix too many of them. So to keep it clean, instead of every time once you need a package, cloning it into the catkin workspace, what we recommend is to create one central Git folder. And then from there, you can symlink to the different catkin workspaces, only the ones that you actually need in your catkin workspace. In this example, you could also as well do it just directly in the catkin workspace. It wouldn't matter technically, but in the future, it's nicer to organize your system this way. That's why we show it this way. Does that make sense? Okay. Okay, so you've downloaded, built, and launched software for ROS. Now we saw in the last command that you used ROS Launch. Launch is essentially a tool to run, instead of typing every time in a console ROS run, you can combine them in one launch file, which informs the system which nodes and which information does it need to load. It's a very convenient tool to run your system. These launch files, and this is important, you'll write one in the exercise, are written in the an XML language and are stored in .launch files. Also, as a side note, if not yet running a ROS Master somewhere, Launch automatically will run this for you. Means you can go into a console, type in ROS Launch, the launch file that you need, and will boot up everything that you need. To start a ROS launch file, like we already did, you would type in ROS Launch and then the name of the launch file. If you already have a package like we had before, so in the first case, you would need to be actually where you launch it, you'll have to be at the path where you want to launch the launch file. If it's the launch file is associated with a ROS package, you can type in ROS Launch, the package name, and then the launch file, such that you don't need to be at this path of the file. It finds it for you automatically. If you want to type in another example, you could do like we had the talker and the listener before. There exists a launch file which launches the two together, and you could use by ROS Launch, ROS EPP tutorials, and talker listener.launch. This guy does the same work you did before, starts the talker and the listener together. Now, if we look at this listener and talker launch file, this is how it looks like. You have in the bottom and the top, you have a launch XML tag, and then you see that we have 2 lines to start the 2 nodes. Each node's tag line specifies which node to run. It has the parameters name. This is an arbitrary name that you can choose to run under which name you want to run the node. And then the PKG, the package name. In this case, it's a ROS EPP tutorial. And then which executable, the type. In the first one, the listener will be of listener type, and the second one, the talker, is of talker type. The output information in the end tells you on where to put the information that it provides. In this case, we say screen, which means you print it on the console. But if you want, you could also say log to put it in a log file if you don't have access to that console. It's a convenient tool to debug. Now, very importantly, once you write your own launch file, you see the difference between here a closing XML tag with launch, and then this sign to close it again. And you have self-closing tag XML tags such as this node, which in the end has this slash at the very end. They mean the same thing, but one is self-closing and the other one can contain elements. Okay, so whenever you'll see an XML error, make sure that you have these tags correctly. Now here's another launch file on the right-hand side. One of the nice things is you can, once you build up a nice launch file, you can reuse it with different parameters. This is where the argument tag comes in play. So in this example, it starts the simulation and has 4 tags, 4 arguments saying use simulation time, which world to use it in debug mode or not, and which physics engine to use. Specify them on the top, like there, and then you can reuse these arguments in your launch file. So in this case, it says if I want to use this argument, if this argument is set to true or false, then also set this parameter. And whenever if you specified it up here, you can reuse this argument by the $ and then slash bracket argument and the argument name, which in these 2 examples also down here. One of the nice things is once you've set up these arguments, you can launch your ROS launch file by ROS launch, the launch file, and then saying argument name equal the value. So you can use the same launch file from the console saying once I want to use the ODE physics engine or I want to use the bullet physics engine, turn on and off different elements. It's a very convenient way to quickly start a certain setup of your node. Okay. This is also an important element. You can nest launch files. So in this example, you'll see that it uses this include tag and then the file. In this case, we want to include this empty world.launch, which launches an empty world in simulation. It doesn't matter. Importantly, in ROS, don't use absolute file path. So if you give it to a friend, it might have a different username, etc. So what we always do is relate it to a package. In this case, it says find and then the package name. I've written here, this gives you the local absolute path, and then you would be in the launch folder, the empty word launch. Now, if this other launch file also needs arguments, we can pass them down by typing in the argument name and then the value. So in this case, we saw that the name would be, for debug, yes or no, would be, okay, the name debug again, and the value is the argument that I got from up there. So you can pass down the values of the arguments from one launch file to the other one. And by including nesting multiple launch files, you can create complex systems that can be launched individually, but also all at once, passing down the arguments. Any questions to the launch file? So you're going to need this in the exercise. Make sure that you make that the XML structure is valid, and then you're going to use the include and the arguments, etc. Now, one of the elements that we'll play around with is the Gazebo Simulator. It's a 3D simulator for rigid body dynamics, and you can include robots, objects, etc. You can also simulate sensors. We'll see that in a second. So this Husky can carry a laser sensor, for example. It provides a 3D visualization, which is also interactive, by meaning you can have a toolbar up here where you can drop in elements such as this box. In the left-hand side, you would see the objects that you dropped and the robot. And importantly, down here, you can start and pause your simulation or slow it down or accelerate it. Gazebo has a database of many different robots, and this Husky robot is a standard robot that comes along with ROS. And Gazebo is essentially a standalone program, but it comes with a ROS interface. And the nice thing is, in the future, if you want to write your own robot, your own sensors, you can include it in Gazebo through plugins. To run Gazebo, you would type in ROS run Gazebo ROS, which is the ROS version of Gazebo, and then just Gazebo as a node, which opens standard empty Gazebo environment. This is the end of the first lecture. There's, for you in the future and now, if you have any questions, you can either ask us, but the internet is full of information. The most important website is probably this wiki.ros.org, where they have documentation and tutorials on each of these topics that we talked about. And then there's the installation website of ROS, and here's tutorials. And you don't want to, in the future, you don't want to reinvent things. So before you start programming something, make sure that you check out existing software. You can do this on the ros.org/browse website, where all the ROS packages are listed. There's a ROS cheat sheet if you need, but you get very quickly into it and you know them by heart, these commands. And for tomorrow, we'll have 2 more links that you'll use, or in the next course. Then we'll have Dominic explaining you exercise number 1.
First of all, let's take a look at the exercise sheet. So what you see here is that they all have always the same structure. So first of all, you see the theory that just Peter covered before. Then there's an exercise part, and at the very end, there's an evaluation. So check these points here. You always see that there's a percentage of how much every point in this evaluation counts. Every exercise has 100%, and there are 5 exercises, so you can get at most 500%. Yeah, so let's start at the top. The goal of this exercise is that you get to know the ROS environment. By first inspecting the simulation of a Husky robot that you've seen before, you can set up the Husky simulation with the link that you see here. There's a good description of what you have to do to get Husky running. And so this only starts Husky in Gazebo, nothing else. So there's no controller, no lasers, no IMU, nothing. Just Husky in the simulation. Then play a little bit around with the ROS Node and ROS Topic commands. such that you can really inspect what's going on. So see the topics, take a look at what are the nodes that are created, what is the setup, how do they interact and communicate. Then clone the teleop twist keyboard. So as I mentioned before, there's no controller running. But with this node, you can steer around the husky with the keyboard. And you could install this from a PPA, or you can clone it. What you have to do is you have to clone it from Git, as you did with the ROS best practices, and then build it from source. If you need a Git cheat sheet, then there's a quick link that you can press on, and you'll just see the very basic Git commands that you're gonna need. Then your last task is that you need to write a launch file, as you've seen before, that XML style file. It has to start Husky in the Gazebo simulation with a different world. So in the directory user share Gazebo 2.2, as you see here, there are some worlds stored. You can pick a world that you want, for example, the RoboCup world. Then you get the nice RoboCup world that you see in the screenshot here. Now I'll quickly take you through the exercise. So I already prepared that launch file. Now Peter explained to you that you can start a launch file by typing ROS Launch, the package name, and then the launch file. But you can also go you can directly start the launch file without the package name, because now you're going to write the launch file, but you don't have a package that where you can put the launch file, right? So you can just create the launch file anywhere in your PC, and then type ROS Launch, and then in my case it's in an internal repository. So I just typed ROS Launch and then the path and the name to the file. And with that you can also start the launch file without having a package. Now then, it should look better on your PC. The resolution is pretty bad, but now you see that it started the RoboCup world, and as Peter mentioned, you can stop the simulation. And now I can drive around Husky with my keyboard. So for the keyboard to work, you have to click on the terminal such that it is active, the window, and not Gazebo. So if I click into Gazebo and then press the keyboard commands go to Gazebo and not the terminal. So that's important. Yeah, so this is the end goal, that you have one launch file that launches Gazebo with a different world plus your teleop twist keyboard node. Then so you can type in all these commands such as ROS node list. Now you see all the nodes running. That's the one that you have to compile from source, so that teleop twist keyboard, and all the others are started with the Husky launch file. Then there's RQt graph that shows you all the nodes and the topics, how they are connected with each other. You see that here there's a teleop twist keyboard node, the one that I use for the keyboard commands. It sends a command velocity that then goes to Gazebo. So that's how I steer Husky. Now you see the evaluation points here. First of all, the Tetop Twist keyboard node has to be installed from source. And how you see this is when you type ROS CD, Tetop Twist keyboard, then it goes into the folder where the source files are stored. And if you would have installed it with the PPA, then this doesn't go into your workspace. It goes somewhere into your system. So I can show this here quickly. ROS CD, Tetop Twist keyboard. I haven't compiled it from source. So now you see here that there's the system path, opt-ROS indigo share. But in your case, there has to be your username, then catkin, workspace source. Then you did it correctly. Okay? So So this is now the ROS homepage. There's a wiki page about pretty much everything that's been developed for ROS. Important is that on top here you have the different buttons for the different versions of ROS. Now we use ROS Indigo and not Kinetic. So we switch there to Indigo, and then so there's some information here about how to use it, how to install it and run it, but we want to install it from source or compile it from source, so we go here to the Git folder, and that's the exact same that you've seen before. You can clone it here. So git clone, and then that part. Now I go into the Catkin workspace source, create, create the symlink. Now you see here that it created that symlink. Now I go back into the Catkin workspace and build it. Catkin build. Now important, after you first build a package, there's always the note at the bottom that says your workspace packages have been changed. You need to resource. So this means that now there's a new package around, and if I would now type in ROS CD Tetop Twist keyboard, it still goes to my system folder because I have not sourced it yet, so it cannot find it. When I now type in source devil in the Catkin, source devil bash source devil setup bash, and now the same command again, ROS CD, and now it goes into Catkin workspace Tetop Twist keyboard. So that's the difference. Now it takes the program that I compiled from source and not the one that was installed.